So last week then we had a look at analysing electronic circuits like this and how we might use Laplace transforms. So quick flip through one slide which talks a little about that. We talked about the Lcr circuit, which is one that we might well have a look at and might be part of your assignment. Some of you might like to have a go at that particular circuit. And we talked about the idea that trying to analyse a circuit like that involves building a differential equation. There it is. And then to actually work out how this circuit is going to behave, we end up having to solve this thing. And that's the solution, which we sort of just arrived at last week. And how you arrive at that is to do with Laplace transforms, and that's what these few weeks are about. So how can you get from a differential equation like that to those solutions? Okay. And we end up finding quite a nice straightforward way of doing it. We did have a look at that function and talked about it by changing the values of the resistance, the capacitance and the inductance in the circuit. You can change the way this thing reacts, and we talked about this being a transient period, so this takes time for this to settle down to its normal state, which for a circuit like this, where we've just got one switch being closed for a capacitor discharging, the normal state is going to be zero charge flowing, so the rate of flow of charge drops to zero, which we might have expected. What we really need to focus on, though, is this use of these Laplace transforms, and it's all about algebra. We're turning integration, which is what we need to do to solve differential equations, into algebra problems. And so we're going to be practicing these sorts of skills over the next week or so. We made a note of this. What the process is, transform each part of our ordinary differential equation, and what we're going to do is think about transforming each part of a circuit, and that's the main aim today actually. It's transforming a network of a circuit into this S-space, transforming it and using Laplace transforms. And then we start manipulating these things, so we're going to be looking at that today. So eventually we can transform back and get a solution. So that's what we're aiming for. Step 2 involves algebra, and we looked last week at the perfect square. We will be looking at the use of partial fractions in this too. So if a solution to a circuit in S-space, and we'll talk about how this can arise, if we get this as a solution, and if you've got your handout handy, did you get one of these? Yep. And turn to page 5 for those Laplace transforms that you had. So looking at that table of transforms that you've got, either on page 5 of the handout or this one that I've just handed out to you now, you can see we've got something on the board here, 5 over x squared plus 7x plus 26. The idea is to get that to look like one of these transforms on the right-hand side. A over s, or a over s squared, or b over s plus a, something like that, where s is the variable that we're talking about. So you can see that in our transform, actually what we would do eventually is swap this x in here for the idea of that being an s. So s squared plus 7s plus 26 looks nothing like any of these. So what we were looking at last week was to try and get it to look like one of these. And we used the idea of the perfect square to get this into the form a omega over s plus b all squared plus omega squared. And if you look at your table of transforms, you can see that actually looks like the damped sine wave, where actually I've used an a, I've swapped the a and the b, but that's the same transform. Okay? And we were looking at this last week. We were looking at transforming something like this to get it into that form, and we had a go at one. And I think I'd like us to start off with the session today by having a look at a couple. Okay, so we'll start off together with the first one, and we'll start that one together, and then I'll let you finish number 1 and have a go at number 2. So if you want to just make a note of those. Okay, so let's start off the first one. 15 over s squared plus 4s plus 29. Ooh. 15 over 4 over s squared plus 4s plus 29. Now,
Take 13 away from the 29 now.
take 13 away from the 29, so we can actually split this into 15 over s squared plus 4s plus, I'll take 13 off that, so that leaves, what's that, does that leave? 8 plus 13. Is that right?
No.
No. 4 plus 25 is what we need to do. We split that 29 into 4 plus 25 from last week. Can you remember why? Make it a perfect square. So what was your thinking, Phil? Remember, yeah, but what we do is we halve the coefficient of s, remember, before we do that. So half of 4 is 2, and square that is 4.
Okay.
So this bit here can now be written as a perfect square. This is all going to be a bit confusing for you, actually, but you need to have a look at that video from last week. I'm sure you'll soon catch up. So how can we rewrite s squared plus 4s plus 4? What's this perfect square form?
S plus 4.
No, s plus 2. Yes. Okay, and we had a look at a few of these last week. I won't review it now, but the video clip there is there for you to have a look at that. So if you're still confused over that, have a look. It's all to do with getting the perfect square. Now I think I left you to sort of finish off a question like this, which was to then work out what the constants were. If we look at this, it looks like the damped sine wave, A or B omega. Well, let's use A omega because I think that's what I was using last week, was it? Over S plus B all squared plus omega squared. It looks a bit like this one. We've got this bit looking right now, look. So we can already say that B equals 2 and that omega squared is 25. So we can find omega is 5. All we need to do now is find out what A is. How do we do that?
You know omega's 5, isn't it?
You do.
15 to 2.
Yep, you've got a little equation you can solve. We've got the A omega.
Oh, sorry, 3.
You changed the letters, Mark.
Yeah, I have. It might be actually. Yet another thing that's confusing you. A omega equals 15 from the top. A omega equals 15. And we know, as Phil says, that omega equals 5. So A times 5 equals 15. So therefore A must equal 3. So we've got our value for A and omega and B. So this looks like, well, this has the form of a damped sine wave. And if you look at your table of transforms, then that's got it looks like this. B e to the minus at sine omega t. Now I'm probably going to confuse my symbols here, aren't I? Because I swapped them round, didn't I? Sine omega t. So I think I might have messed up here. Have I?
Minus
Yeah.
BT, not AT.
Yeah, I think I've got these the other way around, haven't I? So that will be A and B. So we can now put in our values. We know that A equals 3, B equals 2, and omega equals 5. So therefore, for this problem, we have the solution A is 3, e to the minus 2t sine 5t. That might be the solution to a circuit. And if we look back to the circuit we had before, at the start of today, then you can see part of this solution is not unlike the one that we've just been looking at. Okay, we've got this exponential factor and some sine function in it. So you can see how we can start to arrive at circuits like this. Okay, let's just quickly review this then. So, how do we do this? For number one, forming the perfect square is the key. So if I've got something like s squared plus 4s, what do I need here to make it a perfect square? I halve the coefficient of s, so it could be s squared plus 4s, I halve the coefficient of s, square that, so half of 4 is 2, 2 squared is 4, that would be the perfect square. Half the coefficient of s squared, which means I can write this as s plus 2 all squared. And if you remember back to last week, if you multiply out s plus 2 times s plus 2, you get back to that form. So that's the process. So this number needs to be 4. So what do? I make that number 4, and that means I've got to split what I've got here by either adding or subtracting something as Phil was talking about to try and get this to be a 4 plus a 25 makes a 29. So then we can write this here, and we're away. Okay, I'd like you to have a go at number 2. So I need to form the perfect square. I need to form the perfect square. Yeah. So half of 6 is 3. 3 squared is 9. So what I need is 10 over s squared plus 6s plus 9 plus 12. So I split that 21 into 9 and 12. So then I can say that this part is a perfect square. And so I can rewrite that as 10 over s plus 3 all squared plus 12. No, s plus 3 all squared. Yep. That means we can immediately write down using this form that A equals 3 and omega squared is 12. So that means that omega must equal the square root of 12, whatever that is. You don't need to calculate it at this stage. Then I can say from the top, the numerator, 10 must equal B omega, using this form at the top here, B omega. So therefore, 10 equals B times the square root of 12, because omega is the square root of 12. So B must equal 10 divided by the square root of 12. So then I can write the solution. And the solution has the form B e to the minus AT sine omega t. So then I can put in the values A, B and omega. B is 10 over root 12. E to the minus A is 3, thank you, sine root 12t. And you could put it into your software immediately like that. Leaving it in this form means, of course, this is an exact answer. As soon as you start putting in numbers, you're rounding it, aren't you? So, okay. Yes, I did. Here we go. Yeah. If you look at this solution, you see we've got a damped sine wave, and lightly damped, we would say this, because we're going through a few oscillations before the thing dies down to 0. And we can, as we'll see, we can change the damping effects by changing the values of these numbers in here. And they are dependent on the values in the circuit, the inductance, the capacitance and resistance. If you look at the next slide, I plotted the second one you've just done. So 2.89, which is 10 over root 12, and omega turned out to be 3.46, which is the square root of 12. So that's the second function, and if you note this one, then that's much closer to just one motion or half an oscillation before it dies down. We're getting close to critical damping, it's called. So by adjusting the values that go in here, we can change the rate at which this thing responds.
Across the bottom there, 1 and 2. Obviously, that's the time, isn't it?
Yeah.
Is that in seconds?
Yeah. Yeah. Okay. Right. So that's what we were doing last week, and that's quite difficult, you know. And those circuits that are involved with that are not straightforward to look at. But part of that process we've now covered, the u to the perfect square. What I want to do now is to actually look at some networks and work out what their Laplace transforms is. The first thing we need is to be able to transform parts of our circuits. And if you look at your transform that I'm giving you, the middle column effectively, electronic components, and also they're in the handout on page 5, you'll see what is the Laplace transform for an inductor. So let's say we have an inductance of 5 millihenries, so this would be 0.005 henries. What would the transform be? S times whatever the value of L is. So if I've got a network in a circuit with an inductance in it, I change the L value to SL, and then it's into this thing called S space. If I've got a capacitor in a circuit, then the transform becomes 1 over S times whatever the value of the capacitance is. And the resistor in the circuit stays exactly as it is. So we just need to recognize if we've got these components in a circuit, an inductor, a capacitor or resistor, in series, in parallel, we might have a couple of capacitors in the circuit, a capacitor and a resistor, an inductor and a resistor. We're looking at different combinations. We need to recognize these transforms. Yep. I want to look at these transforms and look at how we can manipulate them algebraically to get them into a useful form, and we can put them into a circuit. So it's not going to be obvious initially how useful this is going to be. What we're doing is, it's sort of like, for the first stage, with a circuit like, and I've got an example here that we'll look at. Let's say a resistor and a capacitor in series connected to some sort of DC input of 12 volts. So the first stage with a circuit like this is to transform the network, and by that I mean the combination of resistors and capacitors, resistors, inductors into S-space, or using the Laplace transform. So our combination start over here. Our combination of resistors, capacitors, etc. into their Laplace transforms. Using the ideas of resistors and capacitors in series and parallel. In fact, resistors in series and parallel, because we're turning them all into effective resistors in this S space. So the first step is to transform these networks, and then use Ohm's law to put the voltage across it and work out what the current is, which will then give us our solution, like this previous one, where we had I equals something. So let's look at this. Yeah, I'm trying to write it like this. I should really be trying to write it like that. It's difficult to write neatly. Yeah. Always got to have an excuse. So we've got this network. Let's put some values on it. A 20 ohm and 10 farad. Start off with some nice easy values, okay? Obviously, in the end, we're going to have to use these ideas, but with much smaller numbers. But let's not try and run before we can walk, okay? Do you get 10 farad capacitors? Okay. Well, we're going to put a 12-volt supply across this thing, so we'll see how it copes. Okay, so what do? Well, we basically just add them up, okay? What would this be in S space?
That's the same.
20, exactly the same. What would this be in 1 over 10s? Exactly right. So we've got 20 plus 1 over 10s. So what is the combination of this? They're in series, so you add them up. So the total or the effective resistance of this circuit, if you like to think of it in that sense, in S space would just be 20 plus 1 over 10s. Okay. What would this be? Let's give an example of 10 ohms and I suppose an equally ridiculous value for the inductance, 5 henries.
They sound reasonable to me.
They do to me actually, but then again I'm not an electronics expert. So what do you think we'd get? That would still be 10. This would be
5S.
5s. So the combination would be no, because we can only add things that are like. So algebraically, you can only leave it as 10 plus 5s. Beware of this 5 and s together. Make the 5 look like a 5 and an s look like an s. Yeah. It does become a real pain, as we'll see when we start to manipulate these things algebraically, confusing the 5s and the s's. I'll try and avoid the number 5. Is one way around it, okay? Yeah, like that, yeah. But I did that on purpose to make the point that the 5 and the s look like each other, Mark. What about this one? Change colour for this one. Parallel combination of a 10 ohm and let's make it a little bit more realistic this time, shall we? A 20 farad capacitor. So I've managed to avoid the number 5. What do you do when you add resistors in parallel? Product over sum for two of them, or 1 over, yep, so product over sum. Let's use product over sum. So, what's the transform for this? Ah, well, yeah, but for capacitors, what we're doing here, Nigel, you're saying opposite for capacitors. Don't forget what we're going to do is transform both of these into S space. So we don't use that idea, we just treat them all as other resistors. In S space, yes. In S space, yeah. Okay? Yeah.
In the notes, they talk about the value of that 5. If we take that 5 Henry inductor there, you say the Z in S space is equal to 5s. So you talk about the impedance of the inductor being 5s.
Right.
Yeah.
So it's, yeah, we are.
Once you turn both of them into an impedance, you can then treat them as impedances regardless of them being capacitive or inductive.
Yeah. Yeah. Okay.
I don't want
No. Yep. Yep. That's right. So in S space, this would stay as 10. This would become 1 over 20s. So if I'm going to combine these two, I'm going to have to write product over sum. So that will be 10 times 1 over 20s over 10 plus 1 over 20s. Now, here comes the algebra. Okay, we don't leave it like that. Basically, what we're trying to do is get a whole number of s's on the bottom. And so let's have a look at how we do that. Just shift this out of the way. So we need to play with this to get it into a usable form. And when we've gone through this example, and I'll show you the steps, you'll hopefully see. In other words, we need to simplify it. So, remember me saying at the start of last week and today, we swapped integration for algebra. So we're going to need to do some algebra now. So let's have a look at this. 10 times 1 over 20s over 10 plus 1 20s. In fact, if I shift this to the side, I might be able to make some little explanatory notes as we go along, because it's the same sort of steps that we use when we do this every time. Right, first of all, we can actually work out what 10 times 1 over 20 is, remembering that 10 times 1 over 20s is the same as 10 over 20s. Little algebraic thing we need to recognise. If you've done maths with me before, we talked right at the start of algebra about 10 times 1 over something, or a times 1 over b being exactly the same as a over b. So we're using that idea, first of all, which means we can write this as 1 over 2s. So we can write 1 over 2s over 10 plus 1 over 20s. Okay, there's a couple of ways, which is why I'm pausing, that you can sort of go from here. I'm trying to think of which is the simplest algebraically way to explain it. If I were to multiply top and bottom of this thing by anything I liked, then that's okay, so long as I multiply everything by what I decide to do. So if I decide to multiply top and bottom by 2s, by s actually, no, by 20s, what we're trying to do is get rid of this 20s underneath here. So if I multiply the bottom by 20s, I also multiply the top by 20s. If I'm multiplying the bottom by 20s, that means both of these terms on the bottom need to be multiplied by 20s. So in other words, all these three terms, 1, 2, 3, need to be multiplied by 20s. And if we do that, we get 20s over 2s over 10 times 20s plus 1 over 20s times 20s. I've multiplied everything by 20s. Yes, but if I'm going to times the bottom by 20s, I can't then times the top by 2s. I've got to times it by the same, otherwise it's... So I times top and bottom by 20s. Why have I done that? Because those two cancel to leave just 1. That's why I do it. So I multiply top and bottom by 20s to get rid of that 20s that's underneath at the bottom. So if we do that, we're left with this, look. This equals 20s over 2s. The s's cancel. 20 divided by 2 is 10 over 20 times 10 is 200s plus 1. And that suddenly looks much more usable. We've got something like s plus 1 on the bottom.
2s is now s squared. It's on the top. 20s.
Yes, but it's not 2s times 20, it's 1 over 2s times 20s. So that becomes 20s over 2s on the top. So the s's cancel. Yeah. Write it down, and then we'll have another look at it. Try this. Two ohm and 2 farad. Work out, follow the steps, come up with a simple form for the network, like the one we've just done. Like that one over here. So first step, we've got 2 times 1 over 2s over 2 plus 1 over 2s. So this step, Adam, 2 times 1 over 2s is the same as 2 over 2s is the same as 1 over s. 1 over s over 2 plus 1 over 2s. 2 times 1 over 2s is the same as 2 over 1 times 1 over 2s. So 2 times 1 is 2 over 1 times 2s is 2s. I'm going to need to avoid 2's as well as 5's, aren't I? Yeah? Which is 2's cancel, leaving 1 over s. 1 over s on the top. Okay? 1 over s. When you cancel, we cancel 2's into 2 goes 1, so it's 1 on the top over 1s on the bottom. So you're not left with just s, 1 over s. The algebra is the real thing here. Now I'm going to multiply top and bottom by 2s. So times 2s, top on bottom. Every term, top and bottom, has to be multiplied by 2s. So 2s over s. S is cancelled, left with just 2 over 2 times 2s is 4s plus 1. Okay. Right. Move on and have a look at another one. We need to sort of just accelerate a little bit now because time is creeping on. And I want to look at a few of these networks and then give you some to have a go at. So Let's try another one. 20 ohm in parallel with an inductor. Let's, oh no, we're avoiding 5, aren't we? 4 Henry inductor and a 3 ohm resistor in parallel. What do you think you'd get? First of all, write down what the S equivalents are. That resistance stays as it is, and this stage goes to just 4S. Yeah, not 1 over 4S, just 4S. So this actually makes this one quite straightforward. Product over sum. Now I can times the 3 by the 4 to get 12 over 3 plus 4S. And I'll probably leave it like that. We are going to be going a step further with these things eventually, because if you look at your Laplace transforms, what can you say about S in all of those?
It's in them.
Yeah, it's in them all. Anything else?
Squared quite often.
Squared, yeah. Is there a number in front of the S? No. So, we don't want 4S. We don't want 4S in there. We don't want whatever it was on the previous page. So what do we do to get rid of the 4 here? Divide everything by 4. Divide the top by 4. Divide both terms in the bottom by 4. What do we get? So if I divide everything by 4, divide the top by 4, divide the bottom by 4, remembering to divide both terms on the bottom by 4, we get, yeah, 0.75 or 3/4 plus S. And now it's starting to look really like a transform. Okay, so it's this algebra that we're seeing. Oh, okay, I'll try that. Yeah. Can't guarantee any success, but I'll try. So let's have a look at another one. So now we've got a resistor, an inductor. Resistor is 20 ohms, inductor 10, and oh no, sorry, I don't want to introduce that quite yet. You don't want to make it too difficult, do you? A resistor and an inductor in series and a resistance underneath, which is more like a real circuit actually, because we don't often get pure inductance. So it will have an inductive and a resistive element to it. So what's the Laplace transform? Yeah, this will be, and that will be. So now we've got to apply the idea of product over sum. Product. So what's the product of what's on the top, which is 20 plus 10s, and what's on the bottom, which is 10, divided by 20 plus 10s plus 10. What could we do with that algebraically? Span the brackets. 20 times 10 is 200. 10 times 10s is 100s over Can I simplify the bottom? 30 plus 10s. I tried to put the s small there, Phil. First time I remembered. That better. One other thing I might do to this. Divide by, well, I can see why you're saying divide by 10s still, but we don't want to get, because if I divide by 10s, yeah, and that's not going to help at all. I can divide everything by 10, certainly, to get rid of some of the zeros in there. So that would become 20 plus 10s over 3 plus s. If I divide by 10, I've got to divide every term, top and bottom, by 10. So that's not too bad. One more, and then I'm going to give you a few to take away with you to have a go at, okay? And so you can just jot these circuits down. Have you got, what you can do is have a look at the site and just get these afterwards and have a go at them, Phil, okay, if you need to go? Yeah. Okay, so let's have a look at the one more, the rest of us then, and then I'll give you some to have a go at. So, and then I think I had, yeah. No fives, thank you, Mark.
Yeah, good luck.
Hi, Phil. So we got 4 ohm resistor in series with a parallel combination of a resistor and inductor. I'm just going to pause this for a minute because you might be able to come up with a solution for this yourself. Work out what you think it would be, and then we'll go through it together. So that's the first step, 4 plus that. Now, looking at this right-hand one, can I tidy that up a bit? Simplify it a little bit? Divide by 4 is a good idea because the 80 and the 4 and the 20. All right. Divide top and bottom by 4. Then I get 4 plus 80 divided by 4 is 20 over 1 plus 4 into 20 goes 5. Oh dear, we've got a 5. Try and make that S a bit smaller.
There's no way to get around it, is there?
No. Okay. Yeah. So now actually I do want to try and combine these things, but I can only add fractions, as Gemma says, if the denominator is the same. So here's the trick. What I do is, and this trick does not only apply to Laplace transforms, this is an algebraic trick to add fractions like this. I want the denominator of this left-hand part here to be 1 plus 5s. So I divide 4 by 1 plus 5s, but I've also got to multiply by 1 plus 5s. So what I do is I write 4 times 1 plus 5s over 1 plus 5s plus 20s over 1 plus 5s. I've multiplied top and bottom by 1 plus 5s to do exactly what you suggested, Gemma, which is to make the denominators the same. Now I can write this as Now I can, because the denominator is the same, I can write it as 4 times 1 plus 5s plus 20s, which is what you wanted to do, Ashley, all over 1 plus 5s. And I'll pause it there. So now I can expand out this top, the numerator. 4 times 1 is 4, plus 4 times 5s is 20s, plus 20s over 1 plus 5s. Multiplying out that bracket. Then I can collect together like terms. 20s plus 20s takes 4tx over 1 plus 5s. Yeah. At this point here, just to check the understanding over this step, I've made the denominators the same here so that I can combine it. If I show you by way of example, you might see. If I've got 2 over 5, which is an ordinary fraction, plus 1 over 5, yeah, okay? And that's the whole reason, is to make this the same so I can then combine them. See you later. Yeah. Yeah. Okay. I would like to now just jot a few down for you to have a go at, some networks, and then we'll call it a night and we'll look at them at the start of next week. So just make a note of these networks. Here. Yes, I could divide top and bottom by 5 here to get that S on its own. Yeah. So, try these networks. Try that.